A gold mirror opens in cold shadow and the oldest starlight pours in. A faint smear appears where nothing should be, vanishing in blue, glowing in red, and whispering of a cliff carved by hydrogen. The James Webb Space Telescope holds its breath as a newborn galaxy steps out of the dark ages, small, lopsided and fast. Gas kindles, dust arrives too soon, and a fragile line leans to the red as if escaping through a narrow tunnel in a neutral fog. Clumps hint at a forming disk, gravity writes in bold, and somewhere deep inside a quiet engine may already turn. First light is not a single sunrise, it is weather, and in this weather one ember becomes a map to the first morning of the universe. The universe rests in a long dim hush. After the first fireball cools, light thins into a pervasive background, and the gases that fill the expanding space turn neutral and dark. No stars burn yet. Gravity gathers matter into ripples and knots too small to shine. The cosmic microwave background becomes a pale afterglow, and beyond it stretches a night that lasts for hundreds of millions of years. In that night the future lives in patient gradients and in minute tendencies for matter to fall inward. The first sparks wait inside the slow collapse of cold, clean clouds of hydrogen and helium. Nothing moves quickly, yet everything moves, and the quiet is not empty but full of readiness. When the first stars ignite, they turn the darkness fragile. Radiation from their short lives pushes back the neutral fog and etches thin bubbles of clarity into the sea of hydrogen. In those bubbles, light can travel farther before it is swallowed. The universe begins to wake not with a shout but with a scattered whisper that spreads and merges until a dawn takes hold. Long after those first flares, a telescope with a gold mirror opens its eyes beyond Earth and sets its gaze on this hushed era. The James Webb Space Telescope is built to find stretched light, the kind that has travelled for most of cosmic history and arrived lengthened into the near-infrared band. Engineers and scientists have chilled its mirror and instruments so the telescope's own warmth does not imitate the signals it seeks. It holds its station and stares at patches of sky where nothing appears to move. In these empty-seeming frames it gathers the faintest drifts of brightness for hour after patient hour, until noise separates from signal and a field of ghosts coalesces into a census of remote, persistent things. A deep field forms as long exposures stack together. At first glance, the background looks smooth, but the smoothness is only a tapestry woven from innumerable threads. Each thread is a galaxy whose light has taken almost the full age of the universe to arrive. A few threads stand out by absence as much as by presence. They fail to appear in the shortest wavelength images where bluer light would show. They appear only in the longer wavelength images where redder light collects. This vanishing act is not a trick of processing, it is a signature of distance. Hydrogen along the path has eaten the high-energy part of the spectrum, leaving a sharp cliff that falls away at a specific wavelength and leaves the rest of the light to continue. The telescope reads that cliff not as drama, but as a simple step a turn in the curve of flux across filters. From such steps an age can be inferred. If the step lies sufficiently far to the red, the source likely belongs to a time when the universe has lived for less than 1 billion years. The scene is astonishing and plain at once. Nothing here looks like a firework. The signals are small, the colours subdued, the forms compact and often unresolved. Yet the meaning is large. The age implied by the step presses against expectations built from earlier surveys. The light suggests that stars have already formed and gathered in significant numbers, while the hydrogen fog is still thick in many directions. That fog matters. It makes the visibility of any distant source a function not just of its own brightness, but of the changing transparency of space itself. Where ionized bubbles have grown, the path opens. Where neutral gas remains, the path is blocked. The map of what is seen is also a map of where reionization advances. The background glow that fills space also carries clues to the timing of this change. The cosmic infrared background, a faint wash produced by countless early stars, and warm dust rises as many first sources ignite. Against that wash, a single remote galaxy is only a pinprick, but a pinprick with structure. Its colour slope, its compact outline, its disappearance from the bluer filters all point in the same direction. The telescope measures these traits with care because caution is the first obligation on the threshold of discovery. Less distant dust-reddened galaxies can masquerade as very distant intrinsically blue sources whose light has been stretched. Cool stars within the Milky Way can mimic compact smudges. Random noise can drift upward and pretend to be signal. The process slows in response. Images are dithered and aligned. Cosmic ray streaks are traced and removed. Backgrounds are modelled with restraint so faint halos are not subtracted away. Neighbouring sources are fit and their wings are accounted for. Only then does the selection of a candidate stand firm enough to carry the next step. That step is to ask whether the step in colour speaks the language of hydrogen at extreme distance, or the language of dust and age at much closer times. It is a simple question with consequences that reach. If the break is real and ancient, then first light is not only visible but busy forming stars at a rate that pushes familiar timelines. If the break is a local deception, then the universe returns to a slower rise. The difference is the difference between a dawn that surges and a dawn that creeps. In this first scene, the narrative rests on the threshold. The James Webb Space Telescope turns deep patience into a map of possibilities. The background glow ceases to be a featureless murmur and becomes a layered record. Small forms appear that should not yet be plentiful. Colours gather that should not yet be common. The hydrogen fog reveals itself not by what it shows, but by what it hides. The sense of order changes. The universe does not explode into clarity. It unfolds, and the unfolding happens faster in some places than in others. The quiet awe that follows is precise. There is no urgency, only the steady recognition that a first sunrise is underway, and that the light of it has crossed almost everything to reach a mirror waiting in cold shadow. Data becomes hint, hint becomes pattern, and pattern invites a question. If this is truly first light, what else rises with it that the current view only suggests? The answer for now remains in the hush, and the intrigue grows from the space between what is seen and what is just about to appear. The deep field forms from patient accumulation, each exposure a small sip of light added to the last until the background settles and the faintest shapes hold steady against randomness. The James Webb Space Telescope keeps its gaze fixed and lets the sky move through subtle drifts while the observatory moves and corrects. Later, careful processing knits the offset frames into a single tapestry, where point sources sharpen and cosmic rays vanish. Out of this tapestry, a candidate emerges by vanishing. In the shortest wavelength images, the place where the source should be looks, blank a clean patch with no measurable flux, while in the longer wavelength images a compact smear appears, with a profile like a tiny galaxy. This pattern is the dropout, a method learned from earlier surveys and now pushed deeper by the sensitivity of the near-infrared instruments aboard this observatory. It begins with colour, which in this context is simply the difference in measured brightness between filters. If the source carries a strong step where the light shortward of a specific boundary is eaten by hydrogen, then the shortest filters show nothing, while the redder filters collect what remains. Photometry measures this pattern with small apertures, then corrects for the light that falls outside the circle, and repeats after modelling the local background, so faint halos from neighbours do not bias the estimate. Tests shuffle the apertures onto empty regions to measure how often randomness alone produces a false detection. The catalogue grows, then tightens as the rules select for extreme dropouts, choosing only those that disappear decisively in the blue and arise consistently in the red. In this winnowing absence becomes evidence. A source that vanishes in the blue can be a distant galaxy, or a closer dust-reddened system, or a cool star within the Milky Way. The shapes help. True galaxies, even tiny ones, tend to look slightly extended, a little broader than the point spread function measured from foreground stars. The profile of the candidate shows the breadth of extension just large enough to suggest a small assembly of star clusters rather than a single star. Colours help as well. Dust reddening often produces a smooth tilt rather than a cliff, while a hydrogen break carves a steep step. The candidate shows a steep step that lines up with the expected boundary for a very large redshift, the term that expresses how expansion stretches light. The probability that a local interloper could mimic this exact step across these filters is not zero, yet it falls when the data are all considered together. In the absence of a spectrum, this is how distance is first inferred with care and with honest margins. The team folds known distributions of galaxy types into a model that tests many possibilities, drawing on templates built from nearer objects and letting the code ask what combination of age dust and star formation could explain the observed colours at lower distance. The best answers prefer the far option. The brightness in the reddest bands joins with the non-detections in the bluest bands to push the solution toward the early universe. Completeness tests inject artificial sources into the images with similar sizes and colours to measure how often such objects would be found, and how often they would be missed because a single detection has meaning only when placed in the context of what might have been seen. These tests show that a real source with the measured properties should be recovered frequently in the red filters and rarely if ever in the blue ones just as observed. The candidate persists across these trials. In images taken at slightly different times and roll angles, the position of the smear remains consistent, and its measured flux scales as expected with exposure time. The field also contains a scattering of faint neighbours whose colours are less extreme and simple. Models of structure formation say that even the very early universe should show clustering, so the presence of companions, while not required, adds a small note of plausibility. Against this careful build of evidence, imagination begins to whisper, but the process still insists on restraint. One last family of imposters can lurk the cool dwarf stars that live in the halo of the Milky Way and can carry colours that confuse. The shape test and the subtle asymmetry of the light profile push against that, and an examination of proper motion between visits shows no shift which would be expected for nearby stars over the months between pointings. Thus the balance tilts toward a remote galaxy. With that tilt, the broader canvas stirs. If even one such object is real at this early time, then similar ones may be common enough to turn a rare sighting into a population, and a population into the seeds of reionization. The dropout method, simple in spirit and rigorous in practice, becomes the doorway. It opens because neutral hydrogen paints the early universe with absorption, leaving behind a telltale edge that can be read across filters like a watermark. In the era when the first stars ignite, that edge marches through the near-infrared window, and the James Webb Space Telescope was designed to watch exactly there. The near-infrared camera provides the deep imaging and the careful color measurements. The mid-infrared instrument adds a longer view that can hint at warm dust or old stars. The near-infrared spectrograph waits ready to turn this colour-based inference into a true distance when the emission lines can be heard above the fog. Until that moment, the map stands as a set of probabilities that favour a dawn time. The candidate carries a compact size, a sharp break, and a brightness that sits just at the edge of what models predicted for such an early age. Each of these traits adds a small weight to the scale. None is decisive alone, yet together they lean the story toward first light. The most striking part is how gently the signal presents itself. There is no blaze, only a smudge that refuses to appear where blue light should be. That refusal turns into a guidepost. The blank in one filter is not a failure but a message, and the dim presence in the next filter over translates that message into distance. In this way, the deep field transforms from a static picture into a stage where absence and presence alternate to draw a timeline. The dropout technique writes the first chapter of that timeline with ink made of missing photons. On the screen it looks like almost nothing, and yet it announces a horizon pushed back toward the first sunrise. The intrigue now lies in what the spectrum will reveal, and whether the same absence that marked the detection will give way to a whisper of emission that locks the distance beyond doubt. Until then, the silence is eloquent, and the candidate stands not as proof, but as a door that the next observation may open. The colours of the candidate settle onto a set of plots where difference in brightness between bands draws a map of physical possibilities, and the point that represents this tiny smear does not land where habit expects. The hues lean toward extremes that argue for light, stretched by a very large factor, yet the slope across the longer bands turns upward in a way that hints at extra emission from excited gas. This combination of a sharp blue dropout and a rising red tail is not impossible, but it lives at the edge of what nearby analogues have taught. In the simplest picture, a very distant galaxy born from nearly pristine gas should shine with a harsh, clean spectrum from hot young stars, falling in brightness steadily toward longer wavelengths once the hydrogen break has removed photons above the critical energy. Instead, the measured colours suggest that after the break the curve brightens again, as if fresh light has been added back into the longer bands. That added light can come from gas lit by the first stars where electrons recombine with protons and radiate in a forest of lines, or where oxygen that has lost 2 electrons flashes in narrow features. These lines can fall inside specific bands at the observed distance and tip the colours upward. The candidate seems to carry such a tip which at once strengthens the case for a fiercely young stellar population and complicates every mass and age estimate that rests on smooth models. A second path to similar colours runs through dust. Dust can redden the spectrum and sculpt apparent breaks, but dust usually smooths. It turns a cliff into a slope, and a slope into a gentle tilt. The present colours show a cliff, not a tilt, and then the unexpected brightness beyond the cliff argues less for heavy dust, and more for a blend of newborn stars and glowing gas. Still, the universe is generous with impostors, and some compact red and dusty systems at much smaller distance can pose as ancient light if their shapes are barely resolved, and their spectra are punctuated by features that interfere with clean colour estimates. The analysis therefore tests models with older stars and thick dust folding in the faint detection limits in the bluer bands as hard constraints. Each trial asks whether any reasonable mixture of age and dust at modest distance can produce a non-detection strong enough to mimic the sharp hydrogen break, while also explaining the rising red slope without invoking gas lines that do not belong at that distance. The likelihood collapses under these combined demands. A different ambiguity hides in the interplay between the hydrogen break and the older stellar break that marks the boundary, where light from stars changes as their atmospheres imprint structure. That older break requires more time to grow than the early universe allows unless an earlier burst of stars formed and died with astonishing speed. The measured colours point to a feature sharper than that older break, and positioned at wavelengths that place the source in the dawn era. Thus, the logic pushes back toward the far option. At the same time, brightness in the reddest bands looks high for a source so small, which raises the question of whether a hidden lens somewhere along the path is quietly amplifying the light. If a lens amplifies unevenly across the source, colours can warp because star-forming clumps and glowing gas filaments then contribute out of proportion. The field is searched for subtle arcs, and for mass that could serve as a lens, and the shapes do not match the classic signs. Yet the possibility lingers as a small uncertainty folded into the margins. Instrument behavior can also nudge colors. Differences in how the point spread function behaves across filters can scatter light outside the chosen aperture more in one band than another, and thus mimic slopes that are not real. The analysis guards against this by matching the effective resolution across bands, extracting flux with models that account for the wings of the light profile, and verifying that choices of aperture size do not swing the result. Background subtraction can erase diffuse halos in one band and leave them in another if the model presses too hard. Here the background is treated with restraint, and tests that place artificial sources in the image recover their brightness without bias. Noise plays its own games, and so the measurements repeat on split halves of the data to test whether a few unusually bright or quiet frames have tilted the outcome. The split halves agree within the expected scatter. With these checks in place, the colours stand as a real signature and not a trick of processing. If the rising red slope is driven by lines from excited gas, then this small system is already seeding its surroundings with photons energetic enough to strip electrons from hydrogen and oxygen, which points to very hot and short-lived stars and a pace of formation that could help carve reionization bubbles. The line contribution also means that simple conversions from brightness to stellar mass will overshoot if they assume only starlight. A galaxy that looks heavy on the basis of red flux may in fact be lighter and younger, which eases one tension and introduces another, because to make lines that strong so early requires either an unusual mix of very low metal stars or additional energy sources such as a compact black hole that already feeds. The first option implies a top-heavy birth pattern in which massive stars form in profusion and die quickly, filling space with the first dust and traces of heavier elements. The second option implies a seed black hole in the centre that heats gas and drives winds perhaps already shaping the fate of the tiny host. Both paths amplify the mystery rather than tame it. The colours alone cannot adjudicate between them, yet they set the stage for the spectrum to speak. The spectrum can separate starlight from gaslight, can weigh the strength of the doubly ionized oxygen lines. Against the hydrogen series can show whether a faint glow from ionized helium appears, which would hint at very hot metal-poor stars, and can reveal whether a small broad component lurks that would betray a young accreting black hole. The frame narrows toward that decisive test, yet even before the lines are heard, the colour pattern has already changed the map of expectation. It shows that the era of first light is not gentle and monochrome, but busy and uneven, with some pockets racing ahead. It shows that absence in the blue is only half the message, and that the companion half is a surplus in the red that carries the mark of gas set alight by intense newborn stars, or by something even more concentrated. The candidate therefore does more than sit at the far edge of a colour plot. It sketches a story in which first galaxies are not simple. They are laboratories where stars' gas dust and perhaps early black holes mix at speed painting colours that make little sense until the mind allows the earliest ages to be both swift and diverse. The intrigue tightens not toward a conclusion, but toward the next step where a whisper of an emission line near the predicted place will either resolve the distance beyond doubt or retreat into the fog, leaving the puzzle to deepen. The step that marks hydrogen's bite begins as a pattern in colours and grows into a demand for a spectrum, because only a spectrum can place the boundary with enough precision to turn a candidate into a clock. The Lyman break, named for the energy at which hydrogen absorbs and removes higher energy. Photons shifts to longer wavelengths as the universe expands and its position becomes a ruler laid along the past. A clean detection of this break in a spectrum gives a distance, but the early universe is not kind to clean detections. The line of hydrogen that often serves as the herald, the Lyman alpha emission from gas lit by newborn stars, is born in a fog of neutral atoms that scatter it, blur it, and often erase it. The search, therefore, proceeds with care. The near-infrared spectrograph aboard the James Webb Space Telescope opens its shutters to the small smear selected from the deep field and spreads its light into a trace. The trace carries the sum of starlight and gaslight and the imprints of matter along the path. At the shortest wavelengths in the trace, the flux falls towards zero, not gradually but with a suddenness that suggests the expected break. Beyond that cliff, the spectrum climbs, and a hint of a narrow ridge appears close to where Lyman alpha should fall if the candidate sits at a time when the universe is less than 1 billion years old. This ridge is fragile. Its strength differs from one extraction to the next depending on how the background is modelled, and while the observatory floats above the bright air glow that troubles ground-based telescopes, it still lives with instrumental noise that must be tamed. The team tests different apertures along the trace, checks whether nearby sources contaminate the signal, and splits the data into halves to see whether the ridge holds in each. The ridge persists but wavers near the edge of formal significance, a whisper too soft to shout distance into certainty. Even if the ridge were stronger, a question would remain. Could a different line at a much smaller distance imitate the expected feature because of the way it sits inside the instrument's sensitivity and the chosen band passes from imaging? Doubly ionized oxygen, for example, can produce bright lines that, when blended with others and measured with low signal, can stand in for more ancient light. The analysis addresses this by asking whether any combination of such lines at modest distance can reproduce both the sharp absence blueward and the measured brightness redward without leaving telltale companions elsewhere in the trace. The match fails. The data do not show the auxiliary lines that would be expected in that case, and the shape of the step argues for the true hydrogen break rather than a masquerade. Yet the spectrum carries more to read than lines alone. The damping wing of the hydrogen absorption, a soft shoulder that extends redward of the break when neutral gas lies not only within the source, but also in the space between galaxies, can in principle reveal the fraction of hydrogen that remains neutral in the surrounding universe. A strong damping wing implies that the fog is still thick, a weak one that the local bubble of ionized gas has grown large. The current data suggest a slope that could be interpreted as a modest damping wing, but the uncertainties are large because the source is faint and the extraction is delicate. Still, the possibility that the spectrum carries a measure of the local transparency adds weight to the view that we are watching a bubble thin and spread. A second sign lies in the asymmetry of the candidate ridge. When Lyman alpha survives to be seen this early, it often shows a profile skewed to the red, because photons slightly redshifted can slip through the neutral gas more easily than those at exact resonance. Outflows from star-forming regions can also shift the emitting gas relative to the absorbing gas and carve a path for redder photons to escape. The tiny ridge in this trace, such as it is, leans to the red, a hint that the source breathes with winds and that its radiation is beginning to shape a channel through its environment. If this interpretation holds, then the faintness of the line reflects not only distance, but the patchy nature of reionization, where windows open unevenly and the first galaxies must push their own escape routes for light. Because the line is weak, the continuum measurement across the break becomes even more important. The continuum is the broad swath of starlight that underlies the lines in its near absence bluewood of the break and firm presence. Redwood mark the transition from swallowed photons to those that can travel. The ratio of these fluxes measured with careful accounting for noise and residual background nails down the position of the break and so the distance. Here the continuum shows itself clearly with a sharp drop that aligns with the expected boundary for a galaxy at a redshift that places it inside the reionization era. The width of the drop across the spectral resolution used matches what the instrument should see when hydrogen along the path absorbs nearly all photons above the critical energy. This becomes the backbone of the case. With the break positioned and the ridge tentatively present, the picture turns to what this means for the physical state of the small system. The strength of the continuum suggests a flood of blue starlight from very hot short-lived stars. The near absence of iron and other heavy element lines argues for gas that has seen little prior enrichment, which fits a scene where the first generations have only just exploded and shared their ashes. The combination hints at a population of massive stars that ionize their surroundings aggressively. If the line is weak because much of the path remains neutral, then the local bubble has not yet grown large, and the photons that escape must do so through narrow corridors, which would explain why even a slight redshift in the emission improves transmission. This paints a dynamic view. The object is not a quiet ember, but a small furnace switching on and forcing back the night one narrow window at a time. Despite this vivid scene, the analysis keeps space for doubt. Calibration uncertainties, small residuals from imperfect subtraction of scattered light, and the possibility of slight contamination from an undetected neighbor can all tug the weak ridge toward or away from belief. To guard against wishful seeing, the team sets thresholds before looking, holds to them, and reports the line as a candidate feature, while the continuum break carries the claim. In this way, the distance rests on the most robust part of the spectrum, while the line serves as a suggestive echo that may strengthen with deeper exposure or vanish under closer scrutiny. Either outcome teaches. If deeper spectra later reveal a strong Lyman alpha line, it means the local bubble is larger, or velocities are kinder than first thought. If the line refuses to appear, it means the surrounding fog is thicker, and the path to visibility narrower. For now, the Lyman break itself stands a cliff in a faint landscape, and it tells a clear story. This tiny galaxy lives at a time when the universe is still learning to let light through. Its own light, harsh and young, writes a step into the spectrum that measures both distance and environment. The step becomes a hinge on which the narrative turns from detection to physics, from this is far to, this is how far, and this is how the fog behaves along the way. That hinge opens the next question with quiet insistence. If this much can be learned from a cliff and a whisper, what will the fuller choir of lines reveal about the building of the first luminous structures and the pace at which darkness lifts? The whisper in the spectrum draws the work inward from images that suggest to traces that decide, and the near-infrared spectrograph stretches the light of the candidate into a delicate thread where each wrinkle might be a line, and each hollow might be the mark of absorption. The instrument chooses a configuration that balances sensitivity against resolution because the source is faint and the line that might reveal distance can be narrow and easily blurred into the continuum. Micro shutters open to admit the target, while a few shutters also open on nearby empty sky to measure background that must be subtracted with caution. The observatory steps through small dithers that move the spectrum across the detector to average out pixel scale irregularities, and then many hours of exposure accumulate into a frame where variance falls and faint structure can surface. The data reduction becomes as important as the photons. Flat fields correct for gentle waves in detector response. Wavelength calibrations align sky and instrument so that positions along the trace map to true energies and careful models remove scattered light that can wash a false sheen across the continuum. The team extracts one-dimensional spectra from the two-dimensional trace, using weights that favor the core of the light profile, while not discarding the wings, because a line can bloom slightly wider than the continuum when gas spreads beyond the starlight. At first pass, the putative Lyman alpha line glints a narrow rise just redward of the expected break, but tests immediately begin to ask how strongly that rise stands against the tumble of noise. The signal-to-noise ratio wavers at the edge of the threshold set before the analysis began, and the team refuses to move the goal because wishful thresholds are the oldest trick that data can play. A false positive can grow from a lucky fluctuation woven through by reduction choices. To prevent this, the spectra are built from interleaved subsets, odd frames against even frames, early visits against later visits, and the line appears in each subset with similar strength, though never with the comfort that would end all doubt. The shape of the rise matters as well as its height. A genuine Lyman alpha line this early in cosmic history often leans to the red with a steep blue edge and a longer red tail, because neutral hydrogen scatters photons near exact resonance and allows slightly redder photons to slip away. The candidate ridge shows the hint of such a symmetry, and the peak sits a little to the red of where a simple, symmetric feature would lie. Instrumental features can imitate a symmetry if a detector column is slightly noisy, or if a residual from a cosmic ray crosses the trace, so the two-dimensional frames are inspected by eye and by algorithm to verify that no scratch, ghost, or subtle edge could have carved the shape. The check passes, yet humility remains the rule. Because interlopers remain a danger, the team asks whether the same rise could be an oxygen line or a hydrogen beta line from a galaxy at much smaller distance. That possibility would drag the sharp break in colors away from the hydrogen boundary into the realm of dust or old stars, and thus would demand companion lines at nearby wavelengths with relative strength set by physics. The spectrum does not show those companions at the required levels, and upper limits on their presence translate into odds that favor the far option again. Still light can fool, especially when gas clumps and dust filaments sculpt a galaxy into regions that contribute unevenly through the microshutter array. Slit losses can change with wavelength if the trace drifts, and that could warp the continuum and give shoulders and dips that suggest physics but belong to the instrument. Tests with artificial sources injected into the two-dimensional frames help here. Lines of known strength are added at nearby wavelengths with shapes that match the expected point, spread along the spectral and spatial axes, and the reduction pipeline is forced to find them or fail. It recovers the injected lines with the correct flux within the stated uncertainties, which builds confidence that a real line would not be erased or inflated. A Bayesian model comparison then weighs two hypotheses. One assumes a continuum with a sharp hydrogen break but no emission line. The other assumes the same continuum plus a narrow skewed line at the place where Lyman alpha should fall. The evidence ratio prefers the line model, but not by a margin that would survive without caution, and so the description remains modest and precise. Meanwhile, the continuum measurement across the break grows stronger with the full exposure time, and that measurement alone places the source within the reionization era. The weak line, if real, adds texture to that placement. It says that the local bubble around the galaxy is opening but still small, that outflows may have shifted gas just enough to let some redder photons escape, and that the patchwork of neutral hydrogen between galaxies still forces most resonance photons to wander and disappear. In parallel, the team compares the spectroscopic inference with the photometric redshift distribution built from the imaging. The Pika lines and the tails of the probability distribution overlap the spectroscopic range, which means the two methods agree within their uncertainties. Agreement does not guarantee truth, but disagreement would demand re-examination of both approaches, so the harmony here becomes a quiet support. The calibrations that anchor the flux scale also matter, because the derived line equivalent width, the measure of line strength relative to the continuum, speaks to the nature of the power source. A very large equivalent width can point to intense star formation in very low metal gas, or to additional energy from an accreting black hole. The present estimate with its broad error bars allows both paths. The absence of strong high ionization lines beyond Lyman alpha tilts the reading slightly toward hot massive stars rather than a black hole that has already ignited strongly, yet the limits are not sharp enough to close the case. Ground-based observatories enter now as partners. Keck and the Very Large Telescope point at the same coordinates, seeking confirmatory glimmers at wavelengths difficult from Earth, but possible under very dry and stable skies. Airglow and absorption in the atmosphere complicate the hunt, and the faintness of the target means that hours of integration are required for even a chance. Early attempts return non-detections or broad upper limits that do not contradict the space-based whisper, but cannot strengthen it. In time, deeper integrations may catch a firmer line, or may show that what space thought it heard was the echo of noise. Until then, the James Webb Space Telescope spectrum stands as the best view, and its story is that the break is real and the line is a maybe. That maybe does real work. It guides models of reionization that must fit a universe where some early galaxies show weak lines and others show none, implying a mosaic of transparency and a dependence on local winds and geometry. It guides expectations for how many hours of exposure are needed to push from maybe to yes, and it suggests that the next target should include those with slightly different colors that might favor lines shifted into cleaner regions of the instrument response. Most of all, it teaches patience inside excitement. A discovery at the edge of detectability is not a failure to decide. It is the shape that truth takes at the frontier. The whisper is not yet a voice, but it is not silence. And in that narrow space the science of the first dawn grows sharper, one careful spectrum at a time. The fog that fills the young universe is made of neutral hydrogen spread across expanding space, and it shapes what can be seen more than distance alone. When the first stars and galaxies ignite, their hard light begins to tear electrons from protons and to carve clearings inside the fog. Each clearing grows as ionizing photons stream into the surrounding gas, but growth is uneven because the sources are clustered, and their light leaks out through narrow channels in the tangled clouds that feed them. The result is a patchwork of bubbles where photons can travel far and broad stretches where they cannot. A distant galaxy inside a large clearing can send a line from excited hydrogen toward the observer, and have that line arrive almost intact, slightly shifted to the red, by winds and by the expansion of space. The same kind of galaxy inside a small clearing sends the line out into a sea of neutral atoms that scatter it in every direction until it loses identity and becomes heat. In this way, reionization, the process by which the fog turns transparent, writes a topographical map on the sky that the James Webb Space Telescope is beginning to read. The spectrum that carries a sharp step where hydrogen eats the blue light also carries subtle slopes and shoulders that can betray how much neutral gas lies between the source and open space. When gas is neutral across a wide range, the edge of the break wears a soft wing that extends into the red. When gas is already mostly ionized near the source, the edge looks abrupt. The candidate under study shows a cliff more than a slope, which hints that at least a modest clearing surrounds it. The faint hint of an emission ridge that leans to the red adds to that picture, because photons that are slightly red of the line center do not hit the strongest atomic resonance, and so stand a better chance of slipping through even if neutral gas still fills much of the path. Winds inside the small galaxy can help with that shift by pushing gas away and letting photons emitted from the far side escape more easily. Yet the universe is not a smooth lab. Patches of neutral hydrogen are fed by filaments that connect halos like strands in a web, and recombination, the reunion of electrons and protons, can refill a clearing if the local sources rest. The balance between ionization and recombination sets a scale for how large a bubble can grow for a given production rate of hard photons. The temperature of the gas matters too, because warmer gas recombines less efficiently. In the earliest bubbles, temperatures can rise as shocks and radiation heat the medium, pushing down the recombination rate and helping clearings to persist. All of these pieces play into the visibility of a single faint line in a delicate spectrum. A line that is easy to see may mean a wide clearing, vigorous winds and a geometry that favors escape. A line that is muted may mean that the clearing is new or narrow, or that gas piles up along the path. At slightly later times, bright beacons with central black holes carve tunnels so strong that their spectra show deep deserts blueward of the hydrogen edge, a nearly complete swallowing of light that offers a measure of the remaining fog. At the earlier era probed here, no such beacon is present, and the task falls to tiny galaxies whose combined influence we must infer from collective light. The background radiation left from the earliest time tells how many electrons the universe met, on the way to now a simple measure known as the optical depth, and that measure argues that reionization unfolds over hundreds of millions of years rather than just a sudden rush. The view from the most distant known black hole-powered beacons at later epochs shows that by the time the universe is a little older than 1 billion years, the fog has mostly lifted because the forests of absorption lines give way to gaps. Between these anchors lies the domain where the present candidate lives, and the messages from that domain are subtle and local. One path toward a clearer reading is to find not one bubble, but several that cluster, because clustered sources can merge their clearings and open highways for light. The deep field shows more than one small object with compatible colors near the candidate, and while that alone is not proof of interaction, it fits the expectation that the first islands of transparency assemble where matter has pooled in excess. Another path is to map the way the fraction of line emitters changes with distance. If fewer objects show strong lines at earlier times, it implies that the fog is thicker. Then, and early surveys with the new telescope already hint at such a trend. Though the fields are small and cosmic variants, the difference from place to place can mislead if taken too soon as law. Radiative transfer, the full accounting of how light travels through moving and clumpy gas, complicates every inference. Photons bounce in and out of resonance. Some slip along corridors opened by feedback. Some drown in pockets where cold gas sits still. The escape fraction, the percentage of hard photons that leak from a galaxy into space, shifts with time as supernovae and winds punch holes in the natal clouds, and as new clouds condense. A single galaxy can change its influence on the fog within a few tens of millions of years, a blink in cosmic terms, and an observation catches only one phase. Thus, the silence or the whisper of a line does not translate cleanly into a global number without careful modelling across many objects. Yet even with these caveats, the picture that grows is one in which the first dawn proceeds in a broken rhythm with brightening pockets that spread until they touch, and where each touch accelerates the rise of transparency. The James Webb Space Telescope contributes by reaching the continuum break for ordinary small galaxies rather than relying only on the rare brightest beacons. That reach allows measurements of the faint shoulders in the spectra and opens the way to estimate how neutral the space is in the immediate neighbourhood of many sources. Observatories on Earth add by chasing longer wavelength lines from oxygen and carbon that diagnose how gas is lit and how metals disperse, because the presence of these lines also shapes the energy budget that pushes the fog back. The Atacama Large Millimeter Array watches the glow from fine structure lines and from dust, and when such signals appear near a candidate that shows a strong hydrogen break, they enforce the view that star formation is already painting the medium with new elements and new cooling channels that make the dance between ionization and recombination even more complex. Against this complexity, one simple image persists. The first sunrise is not an even sheet of light, but a lace of bright holes in a dark veil. The candidate galaxy lives inside one of those holes, perhaps near its edge where light fights with fog and winds by a small margin. The line that may be present is a traveller that found a tunnel. The continuum that surely is present is the flood behind that traveller. Each new detection of a break at extreme distance marks another hole, and the pattern of those holes, when enough are mapped, will reveal the skeleton of structure at the birth of starlight. For now, the fog still claims most of space in the era of interest, and that very dominance heightens the wonder that any light gets through at all. The neutral hydrogen does not merely hide the early universe, it reveals its shape by the way it denies and permits, and the denial and permission together become the instrument by which a gold mirror waiting in cold shadow reads the first map of dawn. The light that reaches the mirror carries the imprint of how quickly stars are being born, and the small galaxy at the edge of sight seems to be making stars at a pace that pulls the timeline tight. The conversion from brightness to star formation rate uses calibrations built from nearer galaxies, where starlight in the far ultraviolet band traces the flood of hot, short-lived stars, and where dust corrections can be estimated from colours and from the faint red glow of warm grains. When these tools are carried to the dawn era, they tell a story that strains habit. The measured continuum beyond the hydrogen break is bright for such a compact source, and even with conservative allowances for possible line contamination, the implied star formation rate sits high for the age of the universe at that distance. If that rate holds for long, the stellar mass would climb too quickly, reaching values that models say should not yet be common. Thus a tension emerges between what the light indicates now and what the growth curve would permit over time. One simple path through this tension is burstiness. Starbirth in small galaxies does not proceed like a steady river. It surges in floods when dense clouds collapse and then ebbs when winds and radiation tear those clouds apart. If the observation catches a flood, the instantaneous rate runs high, while the time-averaged rate remains modest. That picture fits with the hints of strong lines and a very blue underlying continuum, both of which can flare during a burst. But even burst must be supplied with gas, and the gas must cool and fall inward against heating and feedback. The cooling time in nearly pristine gas can be short enough to sustain cycles of collapse and dispersal, especially when supernovae have only begun to salt the medium with heavier elements that open new cooling channels. In this way, a duty cycle of violent brief episodes can build mass without violating the global timeline. A second path lies in the initial mass function, the distribution of stellar masses at birth. If the earliest stars form in a pattern that favours massive hot short-lived stars more than in the nearby universe, then a given star formation rate produces more ultraviolet light per unit mass than the usual calibrations assume. The rate inferred from light would then be overestimated if one quietly applies a present-day mass distribution. A top-heavy initial mass function feels plausible in nearly metal-free gas because cooling is less efficient and fragmentation may produce larger clumps. Yet the evidence remains indirect, drawn from colours and line strengths, and the absence of heavy element features. A third path calls on dust, or rather on the lack of dust. If the earlier systems carry very little dust, then very little ultraviolet light is hidden and re-radiated in the infrared. The observed ultraviolet brightness would then sit closer to the intrinsic value, reducing the size of the correction and sharpening the tension rather than easing it. However, some dawn galaxies already show signs of dust through longer wavelength detections, which complicates the picture because even small amounts of dust arranged in clumps can allow bright escape channels while still hiding a great deal of star formation elsewhere. Geometry matters as much as content. In the present candidate, the red slope and the faint hints of warm dust do not demand heavy obscuration, so the high rate looks more like a real feature than a mirage created by selective extinction. A fourth path considers lensing. If mass along the line of sight gently amplifies the source without leaving obvious arcs, the flux would be boosted and the inferred star formation rate would be too high. Weak lensing is difficult to prove for a single object, but statistical studies can estimate how often such boosts occur for sources at these distances and brightness levels. The estimated probability of a large magnification without visible lensing signatures is not high, though it is not zero. In the balance of explanations, lensing can shave the edge of the tension, but is unlikely to erase it. A fifth path points to the way models translate colours into ages and masses. Strong emission from gas can fill broad photometric bands and mimic older starlight, if unrecognized, inflating the apparent mass and thus altering the inferred growth curve. The spectroscopic hints of gas lines in the red bands mean that templates must include nebular emission when fitting the spectral energy distribution. When this is done, the stellar mass typically falls and the apparent age shortens, bringing the ratio of star formation rate to mass into a range that still feels aggressive but not impossible. The galaxy becomes lighter and younger at the cost of demanding even hotter stars or an additional power source to explain the strong lines. That trade reinforces a vision in which the first systems live near the edge of physical extremes, with intense radiation fields and fast winds that keep the engine running. Timescales sharpen the pressure. The universe at this distance has lived for only a few 100 million years. To build up a noticeable mass of stars by then, a small halo must have converted a significant fraction of its gas into stars with high efficiency, or must have assembled early from even smaller seeds that formed stars quickly. Simulations of structure formation can produce such histories in the densest peaks of the initial field, yet those peaks are rare, and the area of the deep field does not cover many of them. The discovery of even a handful of such vigorous objects therefore pushes models to populate the early web with more rapid assembly, or with altered physics of cooling and feedback. It also pushes observers to ask whether selection effects are at work. A survey that selects on brightness in the red bands will favour bursts and objects with strong line contributions that lift the flux in those bands, so the catalogue may overrepresent the most active phases at the expense of quieter stages. This does not erase the finding, it clarifies what the sample means. The candidate becomes a member of a class that trace the high end of the activity distribution at the first dawn. The consequences for reionization are direct. A universe seeded with many such bursts can pump ionizing photons into the fog at a rate sufficient to carve clearings that grow and merge within the allowed time. If instead only a few such objects exist, and the typical galaxy shines more modestly, then the photon budget tightens, and one must count on small galaxies below the detection limit to carry much of the load. Current data begin to favour a mixed picture, where bright bursts like the candidate contribute disproportionately but do not work alone. The clocks that measure ages, masses and cumulative star formation therefore disagree slightly, not because one is wrong, but because each reads a different moment of a variable life. The way to reconcile them is with a history in which the pace stutters, the mass builds in steps, and the light we see now is the crest of a surge. In that crest, the star formation rate looks too fast for comfort, and it is because comfort belongs to smooth curves, and the early universe does not respect smoothness. It respects gravity, cooling, explosion, and chance. And from their interplay a faint smudge emerges that glows brighter than expected, and reminds the models that nature does not negotiate with our preference for steady growth. Dust appears too soon. In a universe only a few 100 million years old, simple pictures expect gas that is clean and nearly free of heavy elements, yet observations begin to show faint signs of ashes and smoke. The James Webb Space Telescope through the mid-infrared instrument hints at a gentle lift in the continuum at longer wavelengths that can be made by warm grains. The Atacama Large Millimeter Array adds a whisper from cold dust and from fine structure lines that belong to atoms heavier than helium, including the line from singly ionized carbon near 158 micron that often marks active star-forming gas. Each clue is small on its own, but together they sketch a scene in which the first short-lived stars have already lived, died, and seeded the medium with tiny solids that catch starlight and glow. This is awkward for comfort, because some channels for making dust ask for timescales longer than the universe has yet lived. The classic factories, the giant stars in their late gentle phase that blow slow winds full of silicate and carbon grains, need hundreds of millions of years to mature and shed their envelopes. The clock has barely allowed that. Another channel, the violent end of massive stars, works quickly. Core collapse explosions can forge heavy elements and send them outward in hot metal-rich flows, where grains condense as the gas cools. Yet shocks in the same explosions can crush grains as fast as they form. The balance between creation and destruction becomes a question of how dense the clumps are, how fast the ejecta cool, and how gently the newborn grains drift into calmer gas. If the dawn carries dust, perhaps the first grains grow not only in the debris of dying stars, but also inside the clouds between stars where metals accrete, layer by layer onto seed particles, turning small cores into larger grains. In a short span, if the gas is dense and the radiation field is not too harsh. The data encourage this line of thought. The mid-infrared slope in a few dawn candidates can be fit with a modest mass of warm dust, heated by fierce young stars. The millimeter detections imply colder reservoirs that absorb much of the ultraviolet light and re-radiate it. When both warm and cold components are present, the picture becomes a patchwork in which clear channels allow bright blue light to escape, while nearby pockets sit smothered in soot. This patchwork explains how a galaxy can look both extremely blue in the near-infrared and yet glow in the far-infrared, because the geometry of clouds and holes matters as much as the total content. Metallicity estimates add tension and relief in equal measure. The near absence of strong iron lines argues that the overall metal fraction is low. At the same time, the strength of oxygen lines in some spectra suggests that local enrichment has already begun. Oxygen tends to appear early because massive stars make it in abundance and return it quickly. Dust that forms out of oxygen-rich gas can be silicate-heavy and can grow fast if the density is high. The presence of dust so early therefore points to a star formation history that includes at least one prior burst brief but intense enough to layer the clouds with the first solids. If so, then the current light rides through a medium already altered by its own ancestors, and the cycle of feedback begins earlier than imagined. Alternative explanations have to be tested because dust is a tempting remedy that can mask simpler mistakes. Strong emission lines from gas can fall into broad photometric bands and fake a warm continuum if the spectrum is not yet well sampled. When templates include these lines, some of the mid-infrared excess softens. Weak lensing can lift fluxes without leaving obvious arcs, turning a small object into a seemingly heavy one with more dust than it truly has. The fields are searched for mass concentrations and the shapes are checked for stretches, and while mild amplification cannot be excluded, it does not explain the full set of clues. Instrument systematics can also play a role. Background subtraction that is too aggressive can remove faint halos in one band and leave them in another, making slopes that mimic grey dust. The reductions are built to be conservative, and split data sets reproduce the trend, which argues that the signal is not a ghost. If dust is present, it does more than change colours. It alters the physics of how stars form. Grains provide surfaces that help molecules assemble. Molecules cool gas efficiently, letting clouds fragment into smaller clumps that collapse into stars. With dust, the path from gas to star quickens, and the mass spectrum of newborn stars can shift. At the same time, dust blocks ionizing light, reducing the ability of a galaxy to punch holes in the surrounding fog unless winds and explosions carve channels. Thus, early dust both enables fast star making and hides the very photons needed to clear the hydrogen veil. The reionization budget then depends on geometry and on the fraction of hard light that escapes through the holes. The presence of fine structure lines carries its own tale. The line of singly ionized carbon often traces dense star-forming regions and correlates with far infrared luminosity at later times. But in the dawn era the relation can bend. High radiation fields can depress the line even when dust glows brightly, leaving a deficit that signals an extreme environment. If a deficit appears along with warm dust, the medium may be unusually hard, perhaps influenced by a central compact engine that heats gas beyond what star clusters alone would do. The seed of a black hole would add heat, and outflows help process grains and stir turbulence that both destroys and grows dust in different corners. The data so far are too thin to separate these influences cleanly, yet the possibility that a small accreting black hole contributes to the far infrared glow is a persistent whisper. Another whisper comes from the shapes of the tiny sources. Some show clumps and faint tails that hint at mergers. Collisions concentrate gas and trigger starbursts, and bursts produce both lines and dust quickly. If the candidate sits in a knot where flows converge, the dust may be the ash of a small early merger, powdered by shocks and preserved in dense pockets that shield grains from destruction until they drift outward. The reality is likely to be all of these at once supernova made seeds rapid growth in clouds geometry that funnels light and perhaps a compact engine that warms the interior. Each piece makes the arrival of dust faster than a single channel would allow. With that speed, the early universe loses the simplicity that models had granted it and gains texture. The texture is not a flaw, it is a map. Dust marks places where stars have lived and died. It marks where gas cools and fragments. It marks where light will struggle to escape and where it will pour through. If the first dawn carries soot, then the very moment of clarity is born amid smoke, and that smoke does not hide the dawn so much as sculpt it. In this view, the puzzle of early dust becomes an invitation to watch how the first cycles of matter and light close upon themselves with surprising haste, and to ask whether the timeline is wrong or merely incomplete. The answer waits in deeper spectra and in more fields, but the question already changes how the first light is imagined not as a clean sheet that brightens evenly, but as a burning edge that leaves charcoal traces even as it reveals the day. Form takes shape inside the haze, and the small source that first announced itself as a dropout begins to reveal a face. The near-infrared images from the Space Telescope carry a resolution fine enough that even at this distance, a compact smear can break into structure when the exposures are deep and the reconstruction is careful. The profiles of known stars in the same field define the point spread function, the standard candle of sharpness, and the candidate spreads wider than that candle in a way that cannot be blamed on motion or on an accidental blur. The light falls with a steep core and a faint skirt, and inside the core the brightness is not evenly round. One side leans brighter than the other, suggesting that the galaxy is not a single clump, but a knot with a companion or an asymmetric concentration inside a tiny disk. Shape measurements dance on the edge of certainty at this scale, yet the patterns hold across filters that probe slightly different rest frame wavelengths, which argues that the pattern belongs to the source and not to a trick of one band. The half-light radius, the distance from the center that encloses half the flux, lands well above the value for an unresolved point, and yet well below that of larger systems a little later in time. In plain terms, the galaxy is minuscule in size, but not a point, and its light is lopsided. That lopsidedness can grow from tides in a merger, from clumps born in a fragmenting gas disk, or from patchy dust that hides one side more than the other. Each possibility has its own fingerprints. A merger often draws thin tails that trail away from the main body, though such wisps at this distance and faintness are almost always lost against the noise. A clumpy disk presents several peaks along a short axis, as if pearls had been threaded on an invisible line. Patchy dust tends to turn the colours uneven across the face. The candidate shows hints of multiple peaks within the core, and a faint elongation that points to an axis with the colours shifting subtly, along that axis bright blue, where light leaks through, and a little redder, where gas and dust thicken. The vector of elongation aligns across the redder filters, which in a more mature galaxy could mark a disk, but here the dynamical evidence is beyond reach. Still, the visible structure invites a picture in which the first small disks begin to form, even while the gas roils from rapid accretion and from the first explosions. In such a picture, the disk is not a smooth plate, but a turbulent sheet where gravity gathers gas into clumps that migrate inward and share their angular momentum with the wider flow, thickening the young system and feeding any central engine that tries to grow. That engine need not be a black hole to start with. A concentration of star clusters can act as a nucleus, and later, if a seed black hole forms or arrives in a merger, that nucleus can cradle it. The asymmetry also fits the landscape of early gas flows. Filaments feed halos along preferred directions, so fresh material does not rain evenly from all sides. Where 2 or 3 streams converge, a wedge can light up, and the telescope then sees a lopsided face because the gas stars and dust are denser along one approach. Simulations of this era often show pinwheel shapes only a few hundred parsecs across, with clumps that shine fiercely for a short time before feedback stalls them and moves the light to another knot. The present object feels like a cousin of those models, a live scene rather than a smooth emblem. Measurements of concentration and asymmetry quantities that summarize how peaky a light profile is and how far it strays from symmetry fall in the regime where clumpy star-forming systems tend to live. The concentration is high, meaning most of the light sits in the center, but the asymmetry is not small, which means the center is not serene. Together they describe a small furnace with sparks that do not line up. In the faint outskirts, a suggestion of a tail appears in one filter and fades in another as if the feature were real, but lost to noise at shorter wavelengths where the surface brightness dips below the threshold. Teams test this by stacking subimages aligned on the same axis and by smoothing at just the level needed to raise diffuse structure without erasing the core, and the tail remains a whisper rather than a statement. Even as a whisper, it adds plausibility to gentle interaction, the kind that triggers a burst without flinging the pieces far apart. A different angle of view asks whether the elongation could be imposed by lensing shear from mass along the line of sight. Weak shear can stretch a source without obvious multiple images, but it should also align many sources in the same direction if it arises from a common mass sheet. The field does not show a clear common alignment, and the mass maps built from visible lenses do not point to a heavy culprit in the right place, so the balance of evidence keeps the shape with the galaxy. Spectral hints can in principle test rotation. If a line crosses the face with a gradient in wavelength from one side to the other, but the current data do not deliver spatially resolved spectra at this size. The single slit or micro shutter collects the whole shape at once. Still, the slight redwood lean of the weak line, if real, could resonate with an outflow on one side, a faint kinship with a breath from a small disk that exhales from its bright limb. Within the core, the peaks separate by a distance that in physical units would be only a few hundred parsecs, at the inferred distance a scale on which star clusters can gather and merge. A chain of such clusters along a preferred direction supports the fragmenting disk view, while a double core with an off-center bridge leans toward a late-stage merger. The data do not force a choice, but they do forbid a picture of a single smooth lump. The turbulence needed to build clumps, this quickly comes free with rapid accretion and with the injected energy from young stars. When gas arrives colder than the virial temperature of the halo, it can dive to the center along streams rather than settling into a hot quasi-static atmosphere, and the result is a sheet of cold gas that buckles and breaks. The instability that governs this break does not require a specific parameter name to act. It is the simple truth that a heavy thin layer under gravity cannot stay smooth when the pressure of motion and the pull of mass fight at similar strength. If a small disk exists, it lives in this unstable regime by design. The face of the galaxy becomes a record of that fight. Clumps mean gravity is winning in places. Gaps mean pressure and feedback have just punched through. Over very short times, by cosmic standards, the clumps can sink and form a bulge. The disk can thicken, and if a central seed begins to grow, it can light the core with soft power that warms gas and alters colors. Even at this stage, there is space for dust to intervene, shading one arm and brightening the opposite where a hole opens. The quiet power of morphology is that it transforms anonymous flux into a specific story. A compact galaxy with an axis with uneven peaks with a possible tail, with color gradients that match the structure is not an abstract data point. It is a system assembling in real-time order, struggling out of chaos, and the struggle is not a flaw, but the engine of growth. This recognition does not solve the puzzle of early mass and bright lines by itself, but it changes tone. The earliest galaxies are not dots that somehow hold too many stars. They are dynamic, clumpy, and perhaps already disk-like objects whose internal motions can feed their centers and spread their light in fits. In that view, the path from first gas to organized structure is short, not because physics is easy, but because the conditions are ripe for collapse and for rapid rearrangement. The image shows that ripeness in miniature are pinhead wide, and yet rich enough to argue that even at the first dawn form arrives quickly, and that beauty is born with violence as its companion. Gravity announces itself in the measure of mass, and the small galaxy that glows so far back in time seems to carry more weight than comfort allows. The conversion from light to stellar mass begins with the spectral energy distribution, a curve that collects flux across many filters, and compares it with families of model galaxies that span ages star formation, histories, dust contents, and initial mass functions. When the measured colours are matched by a very young, very blue population, the required mass to produce the observed light can be small. When the colours show a red lift in bands where older stars or warm dust might contribute, the mass can rise. Here the situation is delicate because gas emission lines likely fill part of the red bands and can masquerade as an older stellar population if not accounted for. When models include these lines, the estimated stellar mass falls from the first high. Guess yet even the careful estimate remains surprisingly large for so early an age. The number is not certain, but the impression is there are many stars in a tiny space, and they did not have much time to assemble. The halo that cradles this system must also be considered because stars live inside dark matter wells, whose depth sets the pace of gas inflow and the resilience against feedback. Halo mass cannot be read directly from the images, but it can be inferred from abundance arguments that ask how many halos of a given mass should exist in a given volume at that time, and whether the observed number of bright galaxies can be hosted by halos that are too small. If the source shines as brightly as measured without strong lensing amplification, it likely sits in a halo heavier than a simple early guess, and the implied efficiency of turning gas into stars during the brief available time presses theories that prefer a slow rise. Another path to a halo estimate runs through clustering the way galaxies group on the sky. Even small deep fields can hint at whether the most distant sources live in biased regions where matter has pooled, and the presence of several candidates with compatible colours in the same small patch nudges the reading toward a heavier underlying structure. Yet the field is small, the variance large, and the translation from spatial pattern to mass carries wide margins. Dynamical masses, the gold standard that uses motion or line widths to weigh a system, are beyond the reach of the present data. Because the spectral line that would reveal a velocity dispersion is too faint, and the spatial extent is too small. Still, one can set bounds. The size is tiny, and the light is bright, which means that for the stars to remain in place against their own gravity, and against the storms of feedback, the total mass inside the half-light radius must be large enough to hold them. A simple equilibrium estimate that uses a characteristic velocity and a characteristic size can provide an order of magnitude, and even with conservative assumptions the inner mass seems significant. If the gas fraction is high, as expected this early, then much of the inner mass may still be gas rather than stars, which only deepens the dilemma. A system that is both gas-rich and star-heavy must accrete and cool at a rate that leaves little idle time. The thought that lensing could quietly amplify the flux without obvious arcs returns here as a potential relief valve. A mild magnification would lower the true luminosity, the true star formation rate, and the true stellar mass. But magnification also changes the apparent size and can distort shapes in ways that the images would reveal with careful stacking of background sources. In the present field, there is no clear sign of a lens strong enough to provide a large correction. Weak lensing remains possible and would shave the edge off the mass but not erase the central impression that the system is heavy for its moment. Dust too can mislead, but in a different direction. If dust hides light, then the true stellar mass could be higher than the uncorrected estimate, not lower. The near-infrared colours do not require heavy obscuration, and the mid-infrared hints of warm dust are modest, so dust does not rescue the models from a high mass. It instead affirms that even a modest mass in dust-bearing gas sits inside. The role of the initial mass function also matters. If the earlier stars are born in a distribution that favours massive short-lived stars, then a given amount of starlight corresponds to a lower total mass than in the nearby universe, because massive stars produce more light per unit mass. This effect pulls the estimate down, which is helpful, but it then demands physical conditions that keep forming very hot stars continuously, and those conditions constrain the gas density, the metallicity and the feedback in ways that are not easy to sustain in a tiny halo unless accretion is very strong. The pace of assembly therefore presses toward extremes. Gas must flow along filaments directly into the central region, cool rapidly and collapse with high efficiency. Feedback from young stars must punch holes for light to escape, but not blow the entire reservoir away. Supernovae must seed heavy elements and dust, while not choking off the next round of star formation. All of this must happen within a span of a few 100 million years. Simulations reach similar scenes in the densest peaks of the initial field, where the early collapse runs ahead of the mean. These peaks are rare, and if several such heavy and bright systems already appear in a modest deep field, it may mean the universe contains more extreme peaks than some models allowed, or that the physics of star formation at very low metal content is more efficient. Another possibility is that the duty cycle of brightness is short, and the survey by good fortune has captured several systems at their luminous crest. In that case, most halos of similar mass would be dim most of the time, and the few caught in burst mode would dominate the sample. That picture reduces the tension with halo counts, because the number of massive halos could remain small, while the number of bright detections is biased upward by timing. The price is a more variable early universe where the first light flickers rather than rises smoothly. There's also the question of unseen companions. If the small source is one bright knot in a larger lower surface brightness structure, the stellar mass could be spread over a wider area that current data cannot resolve, and the image would understate the true size while overstating the density. Tests that look for faint halos in stacked images and that use conservative background subtraction have not revealed a convincing extended envelope, yet the possibility remains at the edge of detection and will require yet deeper exposures to discard. In the end, the mass feels heavy because several lines of inference converge. The spectrum demands a young distance. The brightness and colours suggest a vigorous population. The size is tiny, which raises the implied density. The counts of similar objects suggest that such systems are not unique. Gravity writes in bold by assembling a deep well early and holding gas dense enough for a furious harvest of stars. Whether this bold script is typical of special peaks or a sign that models must widen their rules remains open. The intrigue thrives in that gap, a universe that allows such heavy compact systems so soon either learn to build fast or learn to hide complexity in simple light. The next steps will weigh the halos more directly, search wider areas to escape the whims of small fields, and sharpen the spectra until motion itself can be read. Until then, the mass of this tiny ancient light remains a challenge and a promise, a reminder that matter races ahead of expectation when gravity finds a head start. The possibility that a mirror in the sky has quietly brightened the distant source commands a full audit, because gravitational lensing can change not only how bright a galaxy looks, but also how large, how structured, and how persuasive. Mass between the observer and the early universe bends light, and can magnify a background object, sometimes splitting it into multiple images, or drawing it into an arc if the geometry aligns with a caustic curve. Even when the alignment is modest, weak shear can stretch the image along a preferred direction and lift the flux by a factor that complicates any attempt to turn brightness into mass or star formation rate. The first test is simple and stern: surface brightness must be conserved. If the source were brightened by lensing without strong distortion, its total flux could climb, but its mean surface brightness should not. The candidate shows a compact high surface brightness core and a faint skirt, and when measured against stars and nearby small galaxies, the core sits on the same locus that unlensed compact sources inhabit. This does not rule out mild magnification, but it pushes against large hidden boosts. The second test searches for neighbours with similar colours and shapes that could be counter-images. Lenses often produce pairs or triplets of images flanking a mass concentration, and even if the images differ in brightness, their colours and small-scale structures often rhyme. The deep field is scanned for such companions within a radius set by the Einstein scale of plausible foreground halos, and no convincing twins appear. The third test traces shear. If a sheet of mass lies in front, many background galaxies will feel a gentle stretch toward the same axis. The orientations of faint sources across the field are measured and compared with the expectation from a uniform mass sheet, and no strong common alignment emerges. This argues against a dominant hidden lens that would act on the field as a whole. The fourth test builds a mass map from what is seen. Visible foreground galaxies with photometric redshifts that place them far nearer than the candidate are assigned halos according to scaling relations with their light, and their projected influence is summed to produce a map of potential. This composite map reveals a few small rises, but no ridge or peak close enough and strong enough to generate large magnifications at the candidate's position. The fifth test looks for flexion, the higher-order distortion that bends isophotes into subtle banana shapes near mass peaks. The tiny size of the source makes flexion hard to read, but the more extended faint neighbours do not show the curling expected near a sharp gradient in potential. The sixth test turns to colour. True lensing is achromatic. It bends light without favouring one wavelength over another. Differential magnification can still change colours if different parts of a source carry different spectra and are magnified by different amounts, but strong chromatic trends across the whole object that correlate with wavelength alone would hint at instrumental or dust effects rather than lensing. The candidate's colour gradients align with its structural axis and with the interpretation of clumps and dust, not with a wavelength-dependent stretch that repeats in all directions. The seventh test searches for a foreground perturber, almost on top of the line of sight, too faint to dominate the field but close enough to act as a small lens. Stacking cutouts centered on faint red galaxies near the candidate does not reveal a consistent excess, and direct inspection shows no obvious interloper within the few tenths of an arc-second that would be needed for a strong microlens. At this resolution, microlensing by stars would affect only a minute patch, and should not boost the entire compact source. Milli-lensing by dark subhalos could create small kinks or multiple micro-images along an arc, but there is no arc to inspect. The eighth test addresses the mass sheet degeneracy by asking what magnification prior is reasonable in a random field at the measured depth. Simulations of a large-scale structure predict a probability distribution for magnification that falls steeply for large values and has a long thin tail. The brightness of the candidate sits where the tail could contribute but does not dominate, which means that while a moderate factor is possible, a dramatic hidden lens is unlikely. The ninth test considers dynamics by proxy. If a bright foreground galaxy were the lens, its own spectrum or photometric redshift would betray its distance and its mass. Candidate lenses within a few arcseconds are examined. One object with a redder color lies a few arcseconds away, but its redshift estimate places it behind or level with the distant source rather than in front, and its mass is small. Without a massive foreground anchor, the case for strong lensing recedes. The 10th test returns to morphology under a lens hypothesis. If the compact source were near a caustic, its structure would be tangent to the critical curve, and its brighter knots would often align along that curve. The observed elongation does not trace a plausible critical line built from any nearby mass peak, and the absence of mirrored substructure across a putative symmetry supports an unlensed interpretation. Even so, the edge cases demand attention. Modest magnification without obvious shear remains possible, and even a factor of 2 would matter for the inferred stellar mass and star formation rate. Differential magnification could in theory raise the contribution of line-emitting clumps and bias, the red bands upward, enhancing the impression of very strong gas emission. The team therefore folds a reasonable magnification prior into the modelling, allowing the mass and rate estimates to shift downward within bounds while refusing to collapse the narrative into a lensing tail that the images do not support. A complementary path tests the reverse question: if lensing were responsible for the brightness, would the underlying intrinsic source be so dim and small that the observed clumpiness would disappear once demagnified? The answer is no. The structural parameters remain in the realm of clumpy compact galaxies even after a moderate demagnification. This reinforces the view that the observed morphology is not a mirage. Ground-based spectroscopy of nearby galaxies in the field adds one more restraint by confirming that the brightest potential lenses sit at distances too far to act. In sum, the mirror in the sky is present in principle for gravity bends every ray, but in this case the mirror seems small. The likely magnification is modest, the sheer unconvincing. The counter-images absent the mass map quiet. The candidate may enjoy a slight lift from foreground structure, but not the kind of hidden hand that would turn an ordinary small galaxy into a false titan. That conclusion does not settle all worries, because even mild magnification can tilt the balance in tight budgets of photons and mass. Yet it clarifies the stakes. The distant source looks intrinsically bright for its size and age, not because a lens has made it so, but because its own engine runs hot. The path forward remains to widen the field, refine mass maps with weak lensing from many sources, and revisit the target with even deeper imaging that could catch a faint arc if one hides in the noise. Until then, the weight of evidence allows the story to rest on the galaxy itself rather than on a trick of alignment, and that choice keeps the focus on the first structures as architects of their own light. The center of the small galaxy may shelter a seed that bends the story toward deeper gravity, a compact black hole young enough to count as a seed and strong enough to leave fingerprints in faint light. The question begins with energy. Starlight from a massive newborn stars can ionize gas drive winds and light emission lines of hydrogen and oxygen with great vigor, Yet some spectral features ask for even harder radiation, the kind that digs into helium and pushes electrons from atoms that resist ordinary stellar photons. A small accreting black hole, even at a fraction of its potential, bathes its surroundings in harsh light that can raise the gas to conditions uncommon in pure star-forming regions. The near-infrared spectrograph searches for these signs by looking for narrow lines from highly ionized species and for any hint of a broad base under hydrogen lines that would betray fast motion near a deep well. The present spectrum is thin but suggestive. The weak ridge near the hydrogen boundary leans to the red as expected from winds and from patchy transmission through a neutral medium, and the continuum remains blue and sharp, which argues for hot stars. Yet the red bands may also carry extra lift from lines that fall into their windows at the inferred distance, including lines from doubly ionized carbon, and from nitrogen stripped of more than one electron. If these lines are stronger than star clusters alone, would produce the balanced tilts toward a central engine. The mid-infrared instrument adds a second clue. A mild excess at longer wavelengths can result from warm dust close to a heat source that raises it above the temperature set by starlight averaged over a galaxy. In nearby dwarfs that host small active nuclei, this warm component often appears without the very large dust masses found in heavier galaxies, and the same pattern scaled down could emerge here. The Atacama Large Millimeter Array offers a third clue in the relation between the far infrared glow and the strength of the fine structure line of singly ionized carbon. In some extreme environments, the line is faint for a given dust luminosity, a deficit that arises when the radiation field is so hard that carbon becomes more highly ionized, or when dense compact regions dominate. A hint of such a deficit, if confirmed, would fit a picture in which a nucleus concentrates energy in a small volume. None of these signs alone is decisive, and the distance magnifies every doubt. Yet together they open the door to a seed. Seeds can arrive by more than one path. One path begins with a very massive star born in nearly pristine gas, which dies quickly and leaves behind a black hole of tens to hundreds of solar masses that then grows by swallowing gas and by merging with its kin. Another path begins with a direct collapse of gas in a halo that avoids fragmentation, producing a black hole thousands of solar masses heavy in a single episode. The second path demands conditions that shut down normal star formation for a time, such as intense radiation that breaks apart molecular hydrogen, and thus should be rare and highly clustered. The first path should be common but start small. Both seeds have to race against time to reach the masses inferred for the bright beacons, seen when the universe is a little older than 1 billion years. If a seed already lights this tiny galaxy even gently, the race may have begun near the starting flag. Feedback from a seed changes gas on small scales. A wind from the center can clear paths through dust and neutral hydrogen, opening escape routes for ionizing photons and shaping the patchwork of reionization. The same wind can heat the surrounding clouds and slow star formation locally, while shocks at the boundary of the wind can compress other clouds and ignite new bursts, a push and pull that leaves clumps in asymmetric arcs. The morphology of the candidate with an elongated core and uneven peaks could hold this imprint, though turbulent accretion without a black hole can also make such forms. Kinematics would help because an outflow driven by a nucleus can leave a high-velocity wing on lines that probe gas, but the current data do not allow such a cut. A different lever is timing. A black hole that eats eagerly produces variability on relatively short scales, while starbursts vary on longer cycles set by cloud collapse and supernova delays. Repeat visits that catch a flicker in mid-infrared light or in line strengths could tilt the balance toward a nucleus. The early cadence of observations is too sparse to make such a claim here, but the plan to return is already part of the strategy, because the first dawn deserves a watchful clock. There is also the question of how a seed would coexist with the demand that many ionizing photons escape to lift the fog. An active nucleus both helps and hinders. It carves tunnels that let light out, but it also builds dust in compact regions where gas cools and metals gather, and that dust can absorb hard light and re-radiate it in the infrared. The net effect depends on geometry and on the stage of growth. A very young seed in a light host may be all channel and little cloak. A slightly older seed may begin to wrap itself in soot. The present object with modest warm dust and very blue continuum sits closer to the first picture. Another subtlety lies in the way a seed can alter the diagnostic line ratios that separate pure star formation from mixed power. In the nearby universe, these ratios are read on clear diagrams, but at the first dawn the relevant lines shift into bands where the instruments and the sky challenge detection. Still, by combining limits on doubly ionized oxygen, singly ionized carbon and hydrogen series lines, one can sketch a box in parameter space where only a hard spectrum fits. The candidate lands near the edge of this box, which is not proof, but is consistent with a source of extra energy beyond clusters. If a seed is present, its mass need not be large to matter. Even a black hole with a mass comparable to a dense star cluster can warm gas and shape colours when the galaxy itself is tiny. Growth at a small fraction of the maximum rate would change the surroundings enough to leave a mid-infrared footprint, and change is what the data whisper. The practical consequence is that early black holes may be common companions to the first galaxies rather than rare anomalies. In that scenario, the earliest phase of galaxy assembly becomes a coevolution with black holes and stars, teaching one another how to share gas and how to pace the build. The promise of this idea is bold. The seeds that will later anchor giant galaxies may already influence the transparency of space in these first moments. The caution is, equal lines are weak, continua faint, and models flexible. The path forward asks for deeper spectra that can catch helium lines, that require very hard photons for higher resolution images that can map dust on sub-kiloparsec scales, and for coordinated observations in the X-ray and radio bands, where a nucleus can leave clearer marks. Until those arrive, the seed remains a possibility that warms the imagination without overruling the stars. The centre is a quiet engine in waiting, or a gentle engine already turning, and either way it reshapes how the first dawn is pictured, not only as clusters in a fog, but as clusters surrounding a small gravity well that learns to feed even as it helps to clear the sky. The framework that has guided the understanding of early galaxy formation tightens under the new light, and the models that have long converted dark matter growth into star birth begin to bend. The James Webb Space Telescope reveals compact bright systems at ages when the standard picture expects only the first modest stirrings. In the standard picture, gravity gathers matter into halos, whose mass assembly follows a predictable climb. Gas falls inward along filaments, and a small, slowly rising fraction of that gas turns into stars as feedback from radiation winds, and supernovae keeps the efficiency low. The relation between stellar mass and halo mass grows gently with time, and the earliest galaxies are expected to sit on the thin end of that relation, still shy and light. The observations instead suggest that some halos convert gas into stars with startling speed, at least for brief intervals, and that the scatter around the smooth relation is not a gentle blur, but a wild spread where outliers may dominate what is seen. The first place to look for relief is in the rules that translate light into mass and age. If the colours are warped by line emission from gas, then masses fall, and ages shorten, and the tension softens. If the initial mass function is tilted toward massive stars in nearly pristine gas, then a given amount of light implies less mass than in the nearby universe, and the tension softens again. If dust is patchy and allows bright escape channels, then the ultraviolet brightness may exaggerate the average pace of star formation, while the hidden bulk proceeds more slowly, and the tension softens further. Each of these reliefs helps, yet each draws a cost. Strong line contamination begs for an engine that keeps gas hot and excited in tiny volumes. A top-heavy initial mass function demands conditions that sustain massive star birth continuously in very low metal clouds. Patchy dust that spares some sightlines while choking others requires geometry that cooperates across many systems. The models can accept these costs, but when all are added together, their bookkeeping begins to look like a stack of special cases rather than a single clean fix. The next place to look is in selection. A flux-limited deep survey favours peak phases. If star formation is bursty, the chance of catching a galaxy near its luminous crest is higher than the chance of catching it in its quieter state, and the census is biased toward the most vigorous slices in time. This bias can elevate the measured median rate, exaggerate the apparent typical mass, and fill the sample with objects that do not represent the mean of their halo class. The models can mimic this by allowing very short duty cycles that rise and fall on times of only a few tens of millions of years, and by acknowledging that a small number of bright bursts can push a population statistic upward. Yet this adjustment also implies that most halos at these ages are dim and hard to find, and that the universe hides much of its early work below the current detection limits. That possibility is acceptable and even expected, but it then asks for a careful integration of the unseen faint population when tallying the photons that reionize the fog, and for a reassessment of how the observed bright few can dominate the narrative without carrying the whole burden. A third lever addresses the physics of gas inflow and cooling. If gas reaches the inner regions of halos as cold streams that avoid shock heating, then it can feed star formation at rates higher than the smooth models assume. If those streams are dense and narrow, they can sustain clumps and disks that form stars vigorously, while winds and radiation blow out along channels without ejecting the entire supply. Simulations that resolve these flows show exactly such behavior in the densest peaks, and the observations now press the claim that these peaks may be common enough to matter. That commonness could mean that the initial conditions have slightly more small-scale power than some reconstruction suggest, or that the mapping from early density to halo abundance is more generous in the relevant mass range. It could also mean that the conversion from gas to stars in very low metal clouds is simply more efficient than the recipes used in the models allow. Each option stays within known physics but asks for firmer numbers. The lure of new physics arrives when these adjustments are not enough. If the oldest bright galaxies are too many or too heavy even after line contamination burst selection, cold flows and tilted mass distributions are included, then the scaffolding that builds structure may need revision. A different cosmic expansion history. A slight change in the nature of dark matter that alters how quickly small halos form, or an episode of early energy injection that speeds cooling are all candidates that theorists explore with caution. Yet the threshold for invoking such departures is high, and the discipline remembers that early challenges to the standard model have often retreated when data matured and systematics were tamed. That memory turns attention to the instruments. Calibrations at the edge of sensitivity can drift. Background subtraction can nibble away diffuse halos and exaggerate compactness. Flat field errors can tilt colors, and subtle differences in point, spread function between bands can bias photometry. Teams have worked carefully to control these hazards, and cross-checks between independent pipelines reduce the risk that a single step has misled all. Still, the community knows to reserve humility for the frontier. The weight of evidence at present favours a reality in which early star formation is more rapid in some places than the smooth narrative predicted, not because the universe changed its laws, but because it exploited those laws in regimes where feedback and inflow interact in surprisingly efficient ways. The strain in models may therefore be a path to richer recipes rather than to a new theory. Even in that conservative reading, the consequences cascade. If bright bursts are common at the dawn, then ionizing radiation may leak more readily. Through the channels they blow, accelerating reionization locally. If dust grows quickly, then cooling and fragmentation proceed faster, altering the initial mass distribution and the pace at which clusters build. If seed black holes are frequent companions, then their feedback changes the escape of hard photons, and may imprint correlations between line ratios and morphology that can be tested. All of these are predictions that the observatories can probe by widening the fields, deepening the integrations, and coordinating spectra across wavelengths. The final pressure point lies in the counts. How many of these extreme objects exist per unit volume at a given epoch? Early tallies suggest more than some models forecast. Larger surveys will either confirm the surplus or tame it by averaging over variance. Until those counts settle, prudence keeps the door open to both possibilities at once: hidden systematics that fade with better data and genuinely swift assembly that asks the models to learn new habits. In that open door, the narrative remains faithful to the role. The voice stays calm, the facts anchor the mystery, and speculation is allowed only to the degree that it sharpens the test to come. The rules are not broken. They are under review by the universe itself, and the review proceeds with quiet authority measured in faint stretched light. The pursuit widens from a single mirror beyond Earth to a network of eyes across the planet and in orbit, each with a different gift, all turned toward the same faint smear that could be a beacon from the first dawn. The James Webb Space Telescope schedules repeat visits that deepen the exposures, rotate the field to change the way light falls on the detectors, and push the spectrum toward longer integrations where the continuum across the hydrogen break becomes cleaner, and small undulations can rise from the noise. The near-infrared spectrograph revisits the suspected line to test whether the fragile ridge endures in new data, and whether its shape tightens into the asymmetric profile expected when neutral hydrogen and outflows sculpt the escape of photons. The near-infrared camera repeats imaging with slightly different filter sets to test how robust the color break remains when the window is shifted, and to probe whether any subtle time variation enters the red bands that could hint at changes in compact ionizing regions or at a quietly feeding seed. While space returns to the field, Earth turns its largest telescopes toward the same coordinates. The twin Keck telescopes on the mountain in Hawaii tune spectrographs to near-infrared windows where the atmosphere allows glimpses between the bands of water and oxygen, and long exposures accumulate under exceptionally dry, steady skies. The Very Large Telescope on the high desert in Chile, with its suite of instruments and adaptive optics that sharpen the air, chases the same delicate features from the ground, mindful that sky brightness and absorption lines in the atmosphere can mimic or hide truths when signals are this faint. Each ground-based spectrum undergoes careful correction for telluric absorption, the imprint of Earth's own air by dividing by standard star spectra, and by modelling the columns of water and oxygen along the line of sight. What remains after this subtraction is thin but instructive non-detections that set firm limits, where a masquerading lower distance line would have appeared if the candidate were an imposter, and marginal ripples that neither confirm nor deny the whisper from space, yet align with it well enough to stand as gentle corroboration. The Atacama Large Millimeter Array adds a different kind of follow-up by listening for cold dust and for atomic fine structure lines that lie in the millimeter band, most notably the line of singly ionized carbon that often traces dense star-forming gas. Short programs first place upper limits, then deeper programs under the driest conditions begin to approach a detection, and even before a firm line appears, the continuum at long wavelength builds a measure of the total energy reprocessed by dust. If a fine structure line emerges, its velocity width and offset from the ultraviolet lines become a way to weigh the dynamical state of the small system and to test whether outflows or inflows dominate. In parallel wide-field optical and near-infrared images on large telescopes, search the surrounding sky for a faint crowd of companions at similar colours, because a cluster of candidates around the target would imply a shared structure, a small proto-cluster where bubbles of ionized gas can merge and carve longer sight lines. Some neighbours appear with compatible colours, but weaker breaks as expected for a hierarchy where the brightest member draws notice first, while smaller kin hide in the background. The Hubble Space Telescope, though older and limited to shorter wavelengths, contributes by providing high-resolution images in the bluer bands where the candidate is not seen, and that absence measured at even finer resolution strengthens the case that the blue light is truly swallowed by hydrogen, rather than lost to poor seeing or to coarse sampling. Together these efforts turn a single detection into an environment, a network of constraints that either triangulate the truth or expose a misreading. Calibration work flows alongside the follow-ups. Teams cross, calibrate the 0 points of images from different instruments, match point spread functions across filters, and compare independent reduction pipelines to ensure that the color break and the red slope do not depend on a single choice buried in code. Artificial sources are injected into raw frames with known properties, then recovered by blind runs to test completeness and to trace biases. Weak lensing maps built from the shapes of many faint background galaxies provide a gently resolved picture of the foreground mass distribution. These maps, even with their limited power at this depth, can rule out large hidden magnifications near the target and guide the search for subtle shear. Simulations provide the mirror work in theory, generating mock skies with galaxies at similar redshift and pushing them through virtual instruments to see whether the observed distribution of colors, sizes and line strengths can be produced without invoking new physics. When the mocks succeed only by adopting bursty histories, strong cold flows and a very hot star populations in low metal gas, the models learn what the data already whisper. When the mocks fail without those ingredients, the failure instructs more than any success. The cadence of observation also turns into a tool. By revisiting the field at intervals of months to years, the programs test whether the source flickers. A small active nucleus can wander in brightness on short timescales. A starburst fades more slowly as massive stars burn out and supernovae clear the clouds. Early revisits show no sharp flicker beyond expected noise, a result that does not rule out a seed, but places it in a gentle phase. In the same cadence, the Space Telescope gathers better astrometry for faint neighbours to test for any proper motion that might betray a nearby cool star masquerading as a tiny galaxy. None move as nearby stars would. The community watches the process with care. Preprints circulate with provisional claims, then revisions arrive with deeper data that firm the break and keep the line tentative, and workshops gather teams to compare methods, share pitfalls, and converge on common standards for declaring a source at the first dawn. The spirit is cautious because humility is part of the craft at the limit of light. Yet the mood carries a quiet thrill because each cross-check that survives strengthens not only one case, but the whole program of reading the first sunrise. In this widening pursuit, every answer splits in two. A deeper spectrum that confirms the break also raises a fresh question about metallicity and dust. A gentle detection at the millimeter band that supports early dust also sharpens the demand for a mechanism that grows grains fast. A map that shows no strong lens nearby leaves the brightness with the galaxy and pushes the models of star formation toward faster tracks. The act of confirmation does not collapse the mystery. It refines it and moves it inward. The face of the candidate becomes clearer. The surroundings gain context and the network of instruments begins to play like a cautious orchestra, each section entering on cue, each phrase adding a layer to the same theme. The result is not a conclusion, but a structure of evidence that can bear the weight of speculation without breaking. The first dawn glimpsed from many angles looks patchy fast, and already textured by dust and perhaps by small engines, and this composite view owes everything to the decision to follow one faint smear, with a world of telescopes until the light itself chooses how much to reveal. Dawn in the early universe does not arrive as a clean line. It arrives as a braided edge where light, gas and gravity pull against one another, and the small galaxy at the center of this narrative stands on that edge like a spark blown sideways by cosmic wind. The measurements now in hand sketch a simple picture that refuses to stay simple. A sharp hydrogen break nails the distance to an era when neutral hydrogen still commands most of space. A faint ridge near the expected position for the hydrogen line leans to the red and hints at escape through narrow windows. Colours rise again beyond the break as if gas lit by newborn stars pours extra light into the red bands. Shapes resolve into a compact core with uneven peaks and a preferred axis, a form that suggests a clumpy disk or a gentle merger in progress. Dust against expectation arrives early enough to glow, not only betraying the ashes of short-lived giants, but also greasing the path from gas to star by cooling clouds and seeding molecules. Each clue points to a universe that starts in fits rather than in a slow climb, and the object becomes a lens through which that restless beginning is seen. Yet every answer opens a deeper question. If the star formation rate is as high as the light suggests, how does the supply stay steady in a halo so small? Cold streams that avoid shock heating provide one way, but their density, their cross-section and their duty cycle must be tuned against fierce feedback that wants to tear the clouds apart. If the stellar mass is already large for the age, how often do such compact heavy systems occur, and are they the early cause of future giants or dead-end sparks that burn fast and fade into quieter outskirts? If dust grows quickly, do grains form mostly in supernova debris, and then grow in clouds, or does a faster unknown path operate under the harsh light of the first clusters? If a seed black hole is present, does its gentle heat merely polish a channel for photons to escape? Or does it soon take command and rewrite the balance of winds and cooling in a host too small to hide from its own center? The surrounding fog offers riddles of its own. The damping wing that softens the edge of the break can measure the local neutral fraction. Yet that measure depends on geometry on outflows and on the chance alignment of transparent tunnels. The absence or presence of a hydrogen line at this epoch reads the size of the bubble and the patience of photons with equal sensitivity and small changes in velocity. Fields turn detection on and off like a shutter. Reionization in this view is not a uniform sunrise, but a slow stitching of holes into a veil until the veil loses coherence and drops. The map of those holes will come from numbers as much as from single cases. How many objects at this distance show clear breaks, and how many of those show lines that escape? How often do warm dust and faint fine structure lines appear together? How often do clumpy disks with axes show up in fields where lensing is weak? Early answers are noisy but lean toward a sky with more bright knots than some models predicted a sky, where cold streams and bursty histories win more often than the smooth rules allowed. Theories adapt by raising efficiencies in low metal gas, by letting initial mass distributions tilt toward heavy stars, by admitting that feedback creates channels rather than walls, and by allowing seeds to join early. Observations adapt by widening fields to tame variance, by sharpening spectra to separate gaslight from starlight, and by coordinating ground and space so that each fragile hint is either repeated or removed. In this steady tightening, the first dawn becomes not a myth of sudden light, but a measured change in the transparency of space driven by thousands of small furnaces that switch on and off out of phase. The small galaxy here has already done more than announce its distance. It has set a scale for structure at a time when distances are short and changes are quick. Its size and brightness together demand densities that can only exist where gravity has found an early head start. Its lopsided core suggests that ordered motion grows in the same breath as turmoil, that disks are not gifts of later calm but children of early chaos. Its dust speaks for the first cycle of birth and death, closing in a hurry while its possible seed proposes a partnership that begins while the host is still assembling. The path forward is clear and crowded. Deeper spectra will hunt for helium lines that require very hard light for oxygen lines, whose ratios diagnose the heat of gas, and for carbon lines at long wavelength that tie ultraviolet scenes to cold reservoirs. High-resolution imaging will seek substructure under the clumps to separate pearls on a string from two cores in collision. Wide-area surveys will count the bright few and the hidden many, and will place this object on a true abundance curve rather than on a lucky snapshot. Models will build mock skies that carry cold streams' strong feedback, and early seeds together not as separate patches, but as one turbulent fabric that can be tested against the mixed reality of colours, line sizes, and counts. If the bright peaks remain many after the averages settle, the rules of early growth will change from default restraint to opportunistic efficiency. If they thin with wider view, the frontier will remind that small fields whisper, wide fields speak. Either way, the dawn retains its mystery because the unknown migrates inward as knowledge grows. Answers about distance turn into questions about chemistry. Answers about chemistry turn into questions about dynamics. Answers about dynamics turn into questions about origin. That is the rhythm of this exploration. A single mirror beyond Earth opens a window. Many mirrors widen it, and the universe decides how far the view extends. The final impression is quiet and exact. First light is not a single sunrise, but a weather of many mornings, local and changeable, full of lanes carved by winds, rooms warmed by clusters, halls shaded by dust and courtyards cleared by small engines. The small galaxy that began as a dropout now stands as a guide to that weather. It shows that the path from darkness to day is both shorter and more tangled than comfort once assumed, and that this tangle is not confusion but design. The narrative remains calm because the cosmos proceeds without hurry. It remains mysterious because the next layer is always narrower and brighter and harder to see. The telescope holds its watch. The field deepens, the spectrum sharpens, and the braided edge of dawn lengthens one more thread. In that lengthening questions sing softly. How often do seeds light this early? How fast do grains grow? How far do cold streams reach? How thin is the fog within a heartbeat of the first stars? The answers wait in stretched light that has already crossed almost everything, and the only act required is to keep listening with patience equal to the distance. The field settles into darkness again, but the darkness now carries structure. The mirror beyond Earth keeps its quiet watch, and the network of observatories returns in seasons, and with each return the same faint source becomes less a rumour and more a character in a larger story. The hydrogen brake stays firm, the whispering line keeps its uncertain lean, the clumpy face holds its axis and uneven peaks, and the red lift continues to hint that gas glows under harsh light. Around it neighbouring smudges gather like small islands, and between them a sea of neutral hydrogen still lies thinning by channels that spread and join. The first dawn, once imagined as a single threshold, now unfolds as weather, in which pockets of clarity drift and merge, and in which structures learn to organize themselves while the veil is still being lifted. The small galaxy speaks for that weather. It builds stars fast in a tiny room, hides and shows dust in patterns that make sense only when geometry is allowed to govern, and perhaps warms a nucleus that is still modest, yet already influential. Every fact it offers narrows the possible histories that led to this light, and every uncertainty it preserves keeps the path open for discovery. Models bend toward efficiency, instruments bend toward sensitivity, and the community bends toward patience, because the early universe answers best when asked the same question many times from different angles. In the end, what remains is a particular feeling, the calm of watching a distant process take shape at its own pace, the clarity of seeing enough to know what to ask next, and the mystery of recognizing that each answer moves the unknown inward rather than away. The mirror holds steady, the sky deepens, the braided edge of dawn lengthens, and somewhere in a pocket already clearing another first sunrise waits for the moment when stretched light will make it real.